Hi, this is Maria Arostegi and I'm going to present SLAYER, a semi-supervised learning approach for drifting data streams under stream verification latency. The work is structured in motivations, proposed approach, experimental setup, results, and conclusions. First of all, our initial premise is that in many real-world scenarios, we cannot assume the availability of true levels after predicting new examples. The extreme case is where the supervision of the levels is never available and is referred to as stream verification latency. Concept drift refers to eventual changes in the received stream data, and it can be classified attending to their speed as abrupt or gradual, or if we do attending to the casuistry by feature or level drift. Therefore, to deal with the gradual, slow concept drift adaptation in the challenges conditions, we present SLAYER, a semi-supervised learning approach capable of tracking the evolution of concepts in the future space and analyzing their characteristics. The importance of dealing with the aforementioned concept can be translated into more than 130 works by analyzing assumptions, methodologies, and techniques. Learning in non-stationary streaming environment can be approached from two different perspectives: active, by detecting a drift, or passive, modifying the model without detecting the drift. The delayed or null supervision of incoming data samples implies the use of different strategies. Semi-supervised learning, when a few level samples are available for initial training, and it allows extracting knowledge from unsupervised streaming data, or active learning, when learning method itself chooses the instance to be learned. Finally, there are many algorithms that contribute for the data stream classification in non-environment. For example, APT, that is a kernel density estimation technique to determine optimal one-to-one match between level and unlevel data, compose a geometric-based framework. First, compose mass label IW, which improves compose. SCARG, a clustering followed by classification applied repeatedly in a closed-loop fashion. Amanda, a semi-supervised density-based adaptation model for non-stationary data. Or TRACE, that is a technique that predicts the trajectory of concept in the future space by means of Kalman filters. So, as we have already said, our proposal is a semi-supervised learning method by using passive strategies, and the drift over the streams are gradual. Initially, from the arrival of the initial set of level instance, SLAYER infers the clusters in which these initial samples can be grouped. And this is done by using k-means together with the elbow method to compute the optimal number of clusters. The calculation of the centroids is done by using the Euclidean distance. Then, with the number of samples per cluster and the radius, we get a rough estimation of the cluster density. And when the next batch arrives, and it's predicted by using one nearest neighbor model, another clustering phase is performed to detect emergence of new clusters or disappearance of others. A matching between the clusters from the previous batch and those arising for the current one is done by using the Euclidean norm. At this point, the densities of the clusters are computed to compare those of the previous clusters to which they are mapped. And this is done to evaluate if any change has occurred. Next step consists of a forgetting mechanism that must be triggered to discard previous knowledge when a change has occurred. To this end, SLAYER attains a finer level of granularity by dividing each batch into mini-batches of equal size. Each mini-batch is clustered by using k-means, and then a distance-based matching is computed to correct the centroid position. So, the position of the centroid, it depends on the number of samples that belongs to the cluster corresponding to the mini-batch, and alpha can be thought as a rough estimation of the average speed at which the label concept moves over the feature space during the batch. When a change is detected, alpha is 0, and when no change is detected, alpha is calculated as a set inversely proportional to the average distance between the centroids of tight clusters that are assigned to a label. Finally, when the last of the mini-batches ends, SLAYER obtains a higher adaptability against drifts over the streams by predicting where the clusters will reside during the incoming batch, and this is done by using Kalman filter. That is a simple recursive system used to calculate the state of a linear dynamic system. So in SLAYER, a Kalman filter keeps track of the estimated positions of the cluster centroids in the feature space. We have used a public repository of non-stationary data streams widely adopted by the stream mining community. Specifically, the repository contains 15 synthetic datasets featuring different drifts changes over the time, including translation, rotation, graphs. In the column labeled as D and L, it refers the number of features and classes respectively. In these datasets, the initial 5% of the samples are assumed to be supervised, whereas the remaining streams instances arrive in 100 batches in chronological order. About the methods used to be compared, we have used a static classifier, sliding window classifier, incremental window classifier, a geometric-based framework, Compose, an interactive weighting approach of Compose, level IW, Amanda, a density-based algorithm with the two versions with a fixed number of samples and the dynamic number of samples, and the SLAYER. The metrics that we have used are the frequential error that allows monitoring the evolution of the model's performance over the time, and the macro F1 that grants the same importance to each label class to mild the class imbalance. The results obtained when comparing the frequential error, a comparison with the naive methods, the static, sliding, and incremental, have the worst results except for 3 datasets. And comparing the two Amanda-based approach with the SLAYER, SLAYER obtains the best score, 10 out of the 15 datasets under consideration, and the fixed version outperforms in 4 datasets. Similar conclusions when analyzing the macro F1. And finally, denser critical distance diagrams can show the average range of the models under comparison across the used dataset, wherein the significant difference are declared when the difference between the average ranks of two models is larger than the critical distance. Unfortunately, the average rank achieved by SLAYER cannot be declared to be statistically significant, mainly due to the relative height value of CD, the critical distance, 2 to 71, that results from the larger number of models being compared. Therefore, this analysis is complemented with the Bayesian analysis of difference between the best performing methods in the benchmark. So, Amanda Fixit version and dynamic and SLAYER. Specifically, we model the probability that one model outperforms another based on the results obtained by each of them over all datasets. One fit, the probability distribution is sampled and displayed in barycentric coordinates. We can observe three regions. First, when the first algorithm outperforms the second one. Second, when the second algorithm outperforms the first one. And the third region is the equivalence region, practical equivalence, when the two methods are similar. A rope parameter establishes the minimum difference that scores of both methods must have for them to be declared different to each other. In this case, the rope parameter has been fixed 0 to 1, and it can be observed that the distribution appears clearly skewed towards SLAYER. When comparing the results of the frequential error with the dynamic, same thing occurs. Finally, SLAYER's goal was to analyze the evolution of clusters and ties them together across the batches so that a correspondence between levels and evolving cluster could be constantly maintained over the time, and this has been successfully achieved. To talk about the future work, we have analyzed 4 possible lines. The first one, to analyze different methods capable of learning topological relationships between multi-dimensional samples, for example, using growing neural gas. Then we can connect different clusters over many batches for which an alternative measure of similarity. Then we can extrapolate SLAYER core's concept to consider online clustering. And finally, we can consider different variable size of mini batches to reduce the computational effort or to obtain more accurate representations or to get a better traceability of the levels. And that's all for me. Thanks for your attention.